Okay, back to projectile motion. In part 1, we took a look at the first 6 out of 10 commandments that will help us answer any projectile motions question we'd face in an exam. We spoke about how important the variable of time is in gluing the x and y motions together, and did our first calculations to find the total time spent in the air by a projectile. In chapter 1, we saw how the initial vertical velocity of our stone helps it gain some initial altitude against gravity, and how this negative acceleration due to gravity progressively reduces this vertical velocity until it becomes 0. Using SUVAT, we found that the time taken for the stone to reach its maximum height was of approximately 1.17 seconds. In chapter 2, we saw how, starting from an initial vertical velocity of 0, gravity begins accelerating the stone downwards in causing the velocity's vertical component to now increase in magnitude, but in the negative direction. In saying that the stone's maximum height reached was a total of 50 meters above the ground, we calculated that the time taken for gravity to accelerate the projectile across this displacement was of approximately 3.19 seconds. Adding these two values of time together, we obtained the total flight time of our projectile of 4.36 seconds. Now, you might be asking, how did we know which SUVAT equations to use? Here's another little trick. Commandment 7. When we are doing y motion calculations, we always want to be using SUVAT equations that have acceleration in them. But why exactly? Well, remember, acceleration due to gravity only acts on the vertical motion. It does not operate on any horizontal motion of the projectile. So, to make sure all our y motion calculations are fair and take all the influences acting on them into account, it helps to know we should be aiming to pick SUVATs with acceleration in them and rearrange those for whatever value we're trying to solve for. Now, hopefully things are making sense so far, but you might be a little suspicious about one aspect of our calculations. In those last few calculations, why did we say gravity and displacement were negative? Well, we said that because values of velocity, displacement, and acceleration are all vectors, and vector values need to be given a mathematical sign that matches the direction in which they're pointing in. But how do we know which directions need to be considered positive and which others are negative? Commandment 8. We set the projectile's launch position as our mathematical origin and orientate all our vectors relative to that origin. Here, if we zoom into our launch position and make that point the origin of a set of axes, we'll see quite naturally that the vectors of acceleration and displacement point downwards into the negative quadrants of our y-axis. If that's the case, when we plug those numbers into our SUVATs, we want to make sure they reflect those directions. Now, if you forget to account for this, the actual numbers you obtain as answers won't be incorrect numerically. You might accidentally get a negative value for something that can't be negative, like time, and then just make it positive for your final answer and get it right. But examiners will be looking out for your full calculations and give marks based on their validity. So be warned. Not accounting for the direction of vectors in your calculations might not deprive you of the mark for your final answer, but you'll probably lose out on a couple of marks for your actual calculation. Okay, so what about the horizontal motion questions we might be asked? The most important thing to remember about the x motion in projectile motion is that horizontal velocity is constant. It does not change from the start all the way to the end of the motion, and nor should it, because as we'd said before, there is no acceleration taking place in the horizontal motion, meaning no change in velocity. This is super useful for our calculations because we can get away with not using overcomplicated SUVAT equations. We can stick to the basic ones, like velocity equals distance divided by time. What it also means is, once we find the horizontal component of our initial velocity at the beginning of any projectile motions question, that component is the same as the horizontal component of our final velocity. It's super important to remember that horizontal velocity is constant because it helps us find the answers to two big questions. What is the projectile's final velocity? And how far did the projectile travel from its launch point? So, if we're trying to figure that last question out, all we need is to rearrange v equals d over t to solve for distance, set our v value as the horizontal component of our initial velocity, and multiply it by the total time the projectile spends flying through the air, which, as we established, came from all of our y motion calculations. So here's how everything connects. You will usually be given the basic raw ingredients of initial velocity, u, the angle of this velocity to the horizontal, which will allow you to break the vector into its components, and the launch height above the ground. Now, before any calculations, we always begin by resolving the initial velocity vector into its x and y components, so we know what numbers we need to use for the calculations in each dimension. After this, it's ideal to begin by finding the total time the projectile spends in the air, so we create for ourselves the bridge between the x and y worlds. If we are then asked to find the maximum height reached, we will need the initial vertical velocity component and the time it takes to reach 0, also known as t1, the time it takes to reach its maximum height. To calculate this time, we'll rearrange the suvat v equals u plus at and solve for t. We then take these numbers and use the suvat s equals 1/2 of at squared plus ut to find the vertical displacement the projectile has managed to reach in this time t1 against gravity. If you're asked to find the total distance traveled, we are going to use the horizontal component of the initial velocity. Remember, this one is constant throughout the entire motion, and the total flight time of the projectile. We can then rearrange v equals d over t to solve for distance and plug those values in to get the value of displacement in meters. If you're asked to find the final velocity, you are really being asked to first find the vertical and horizontal components of this final velocity vector, and to then use Pythagoras to combine them into v final. Remember, you already have one of these two final components, the horizontal one, as it's exactly the same component as the one for initial velocity u. So essentially, the only calculations you ultimately need to do are in finding the y component of the final velocity. To do this, take time t2, the time taken for the projectile to go from its maximum height to the ground, and use the suvat v equals u plus at, remembering that u is 0 here, since we are starting from the projectile's maximum height. This will give you the vertical component of the final velocity. Now that you have both components for final velocity, we can use Pythagoras to combine them together and give the magnitude of the final velocity vector. If you're asked to give the angle to the horizontal of the final velocity, use right-angle trigonometry, SOHCAHTOA, to find the angle between the hypotenuse, also known as the actual final velocity vector, and the velocity's horizontal component. So, remember, projectile motions questions are designed to require a couple of steps to go from raw ingredients to the final answer the examiner might be chasing. If we know this about the questions going into them, as long as we follow the right opening moves of resolving our vectors, finding the glue between the x and y dimensions, time, and remember these 10 rules, we'll have everything we'll need to pick the right suvats and get full marks for any variation they might throw at us. Hope that helps. For more videos and resources like this, head on over to mstutoring.com. And as always, thanks for watching.